We will be talking about Menelaus theorem today.
All right, so what is Menelaus' theorem? This theorem states that given a triangle ABC, if line DF intersects line AC, where F is on AB, D is on the extension of BC, and E is on the intersections of DF and AC, then you will have two cases arise, with case A being the absolute distance and case B being the signed distance. So case A states that the absolute value of BD over the absolute value of DC multiplied by the absolute value of CE over the absolute value of EA, multiplied by the absolute value of AF over the absolute value of FB, all yields a product of 1. And then case B is essentially the same thing, just without the absolute value signs. So we have BD over DC multiplied by CE over EA, multiplied by AF over FB, and that equals a product of -1.
So who was Menelaus? He was a Greek mathematician and astronomer. He lived during the 1st century AD, and Pappus and Plochus both called him Menelaus of Alexandria.
All right, so before we get into the proof of Menelaus' theorem, there are some important concepts and ideas that we need to discuss that are going to be utilized in the proof. So one of those is going to be parallel lines. So two lines are said to be parallel when they never intersect each other, even when these lines are infinitely expanded on both ends. Another important idea is that of vertical angles. So vertical angles are formed when two lines intersect each other. This results in 4 different angles being created, and the two opposite angles are equal to each other. This is because all angles on a straight line add up to 180. So for example, if we pull up angles 1, 2, 3, and 4, we see that angle 1 plus angle 2 should add up to 180 degrees. However, angle 1 plus angle 3 should also add up to 180 degrees, because both of those angles are going to be on a straight line. And so this leads to the conclusion that angle 2 and angle 3 must be equal to each other, and so those opposite angles are equal, and then same thing can be said for angles 1 and 4. So now we have transversals. A transversal is a line that intersects two lines at two distinct points. And then we also have a special case of transversals, and this deals with parallel lines. So a transversal intersects two lines, and then in this specific case, it's going to intersect two lines that are parallel to one another.
So then we will have also interior and alternate exterior angles. So for alternate interior angles, it is a pair of angles inside a parallel line that has been intersected by a transversal that are alternate positions from each other. So for example, AD and angle are equal to each other, and then angle C and angle B are equal to each other. So then for exterior angles, it is a pair of angles outside the parallel lines that are alternating positions, like angle 1 and angle 4, and angle 2 and angle 3.
Alrighty, so now we have corresponding angles. So in the same situation where we have parallel lines, corresponding angles are formed on the same side of the transversal, and they have relatively the same position with respect to the transversal. So for example, angle 1 and angle 5 are equal to each other because they are both to the left of the transversal, and they're on top of the parallel lines. And then similarly, we have angles 2 and 6 equal to each other, angle 3 and angle 7 are equal to each other, and angle 4 and angle 8 are equal to each other. Now we can discuss similarity among triangles. So two triangles are similar if they have the same shape but are of different sizes. So triangles are defined to be similar if all 3 of their angles are equal to one another. This leads to something called the angle-angle similarity criterion. So we can say that two angles suffice for similarity, because if we look at these two triangles, the congruency lines indicate that angle A equals angle X and angle B equals angle Y. We know that the 3 angles of any given triangle need to add up to 180 degrees. Therefore, in triangle ABC, angle A plus angle B plus angle C is equal to 180 degrees. Similarly, in triangle XYZ, angle X plus angle Y plus angle Z all add up to 180 degrees. Therefore, we can conclude that angle Z must equal angle C. So if we know that two angles of two different triangles are equal to each other, then all three angles must be equal to each other as well, and the triangles are similar.
So then we have the triangle proportionality theorem, which states that if a parallel line to one side of a triangle intersects the other two sides in different points, then it divides the sides into proportional corresponding segments and angles. So the proof for that is we have a triangle that is ABC with a parallel line to BC that is PQ. So from that, we can say that angle APQ is equal to angle ABC, and angle AQP is equal to angle ACB, since these are corresponding angles from the parallel lines. Due to those two angles being similar to each other and equal to each other, we can then say that the triangle PAQ is similar to the triangle BAC by angle. From those two triangles being similar, we can then say that side AP is equal to AB, and then that is proportional to side AQ over AC, since the corresponding sides are similar triangles of proportional. Due to all of that, we can then say, in another way of saying it, that PA is over BA and QA is over CA. So then we will have absolute and sine distance, which is our two cases. So absolute distance refers to the physical separation between 2 points that is always positive and does not account for direction or in which way a line is oriented. Whereas sine distance refers to the separation between 2 points that can be negative or positive, and this takes into account direction. If we have two lines, one can be positive and the other can be negative.
So to further elaborate on sine distance, we can imagine a line, and then it's going to have 3 points, A, B, and C. So if we focus on the line segments AB and BC, we can see that the arrow is pointing in the opposite direction. So this means that focusing, now we have segments BA and BC. And then because they point in the opposite direction, they will have opposite sign values. So for example, if the right direction is a positive direction, then BC will be positive and BA will be negative because these two lines are going in the opposite direction. So to further emphasize, BC does not equal CB, because BC is going to the right, however, point C to B is going to the left. So they would be, they would have the same value just of opposite signs. Okay, so now to get into the proof of case A. So we can have our triangle A, B, and C. And then we have the extension DF and point E is on AC. So let us draw a line XC, which is parallel to AB. Now, DF acts as a transversal between the two parallel lines. Angle EXC is equal to angle AFE because these are alternate interior angles, which again arises because we have the two parallel lines. Now, angle ABC is equal to angle XCD because these are corresponding angles. And angle BFE is equal to angle DXC because these are alternate exterior angles. Therefore, we can relate triangles FBD and XCD by similarity criterion AA. This implies that the absolute value of FB over the absolute value of XC is equal to the absolute value of BD over the absolute value of CD. And then for the sake of this proof, we are going to label this equation as equation number 1. All right, so continuing with this proof, we see that angle FEA is equal to angle XEC since these are vertical angles. Now by angle, triangle EAF is similar to triangle ECX. This implies that the absolute value of CX over the absolute value of AF is equal to the absolute value of CA over the absolute value of EA. And then we are going to label this equation as equation number 2. Now, if we multiply equations 1 and 2 together, we're going to get the following, which basically says that the absolute value of FB over the absolute value of CX multiplied by the absolute value of CX over the absolute value of AF is equal to the absolute value of BD over the absolute value of DC multiplied by the absolute value of CE over the absolute value of EA. And then on the left-hand side, we can go ahead and cancel the absolute value of CX. And that leaves us with the absolute value of FB over the absolute value of AF is equal to the absolute value of BD over the absolute value of DC multiplied by the absolute value of CA over the absolute value of EA. And then if we multiply the left-hand side by its reciprocal to move it over to the right-hand side, we will get that the entire product yields 1, which is the completion for the proof for case A.
So then we have proof B, which is the sine distance. So we once again have our triangle ABC with the extension of CD and the transversal of DF with the intersection point E through AC. And then we can say that the extension of CD is moving in a negative direction. So we can once again say that we can draw a line XC, which is parallel to AB. DF acts as the transversal between the two lines. So then we have angle EXC is equal to angle AFE, since these are alternate interior angles by those parallel lines. And then we have angle ABC is equal to angle XCD, since these are corresponding angles. And then we have angle BFE is equal to angle DXC, since these are alternate exterior angles. So by those angles, we can then say that triangle FBD is similar to triangle XCD by similar criteria angle, which states that FB over XC is equal in proportion to BD over the negative of CD. We will once again use this equation as -1 as we keep going through our proof. So continuing our proof, we now also have angle FEA is equal to angle XEC, since these are vertical angles. By that angle and a previous angle, we can know that similar triangles are formed by triangle ECX being similar to triangle EAF by angle criteria, which then leaves us with the proportion of CX over AF being proportion to CE over EA, and we will use this as equation 2. So when we multiply the equation 1 by equation 2, we get FB over CX is times CX over AF equaling to BD over negative CD times a CE over EA. We can once again cross out CX and rewrite it as FB over AF is equal to BD over negative CD times CE over EA. We can multiply and do the reciprocal of FB over AF to now make it B. The equation of BD over CD is times CE over EA times AF over FB, which the product of that equation will make it be a -1.
All right, so those were the 2 proofs for cases A and B for Menelaus' theorem. And then this slide contains the sources that were utilized for the information on the slides, and they are labeled numerically, and the source that was used in each slide can be found on the bottom of the slide. Thank you.